Hey physics friends, let's take a look at this workbook page about gravitational potential energy. It starts off pretty simple. It asks us where the gravitational force this astronaut will experience will end up being zero. This is a pretty straightforward situation, but if in more complicated situations, it's sometimes useful to look at a free body diagram in each region of space. So if she's to the left of both of them, both forces pull to the right. If she's in the middle of them, one force is going to pull to the left, one force is going to pull to the right. And if she's on the right side of both, then both of them are going to pull to the left. So obviously, it should be somewhere in between the planet and the moon, right? Because that's the only place where the two forces even have a chance of balancing out. Okay? To make them balance, since the planet is so much bigger than the moon, we're going to have to scoot real close to the moon in order for those forces to balance out. For part B, this is almost a trick question. We're saying if we move the planet, how does that affect the gravitational force between the astronaut and the moon? To which the answer is, well, it doesn't, right? There's nothing in the equation that involves the planet as long as we are talking about the gravitational force on the astronaut by the moon, right? Forces come in pairs. The planet doesn't have anything to do with that particular force pair. Had this question asked about what happens to the net gravitational force on the astronaut by both objects, that would obviously be a different story. So, for the next part, this is the part that I wanted to talk about the most. This is going to require a little bit of background information in order for this to make sense. So we know that if something goes higher, its gravitational potential energy increases, right? We've been working with conservation of energy and MGH as our gravitational potential energy, and everything's been cool, except you technically can't do that if your G is going to change, right? As our little bow tie satellite gets higher and higher, the gravitational field that it experiences is going to get less and less. So that's not going to be as easy as it usually is. We can look at the formula chart and see if there's anything there to help us out. And there is. That looks useful. It looks a lot like the gravitational force equation, like the Newton's law of universal gravitation. There's only a single r in the denominator, not an r squared, which, knowing that energy and force times distance, that should check out. But really the baffling thing here is why is there a negative sign? And this has to do with math, right? And this has to do with a convention that physicists have set up in order to make this kind of planetary plus scale idea of gravitational potential energy work. So imagine far, 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 far away, at r is equal to infinity, physicists have defined this point to be where our gravitational potential energy is equal to zero, right? When we do stuff, in the lab and we work with MGH, you have the luxury of choosing where h equals zero, where your reference point is going to be, all right? So mathematically speaking, it makes sense to choose essentially, quote, h equals zero at r is equal to infinity. So what that means is that technically all gravitational potential energy, when we're talking planetary scale or bigger, technically it's always negative, right? So 0 is the biggest number that you will get. And so as you get then closer and closer to your planet, your gravitational potential energy is going to become super duper negative. So I've kind of looked back at my picture and I've assigned some totally arbitrary, not at all accurate values for the gravitational potential energy at a few different heights, right? So thinking back, right, looking at our little bow tie satellite, right, we start in a low orbit and we move up to a higher orbit, right? We figure that, well, I think UG was supposed to increase because it technically did get higher. Does that check out with this whole negative UG thing, right? And it does. right? When we are close to the surface, our gravitational potential energy is super duper negative, right? As we move further away from the planet, it becomes less negative. So it's kind of weird, but a less negative number is technically an increase. So that checks out mathematically. And the whole reason why we do this in the first place is going back and actually now reading the question, right? This has us focusing on what's called escape velocity. So in order to escape like the gravitational field of a planet, technically you have to go infinitely far away. All right, our formula for gravitational field, you see I've written it there on the right. All right, gravitational field is equal to gm over r squared. Well, g isn't zero. The mass of the thing you're trying to escape isn't zero. All right, you can't really let your gravitational field ever go to zero, but you can get really, really close. Okay, as your denominator approaches infinity, it's going to make your fraction smaller and smaller and smaller and smaller. All right, so this kind of goes back to that idea of let's let this r equals infinity be like a really convenient point for us in terms of like reference. So long story short, our big idea here is our equation for escape velocity. Okay, escape velocity occurs whenever your total energy is equal to zero, which only makes sense if you can consider gravitational potential energy to be negative. So this is even an extra complicated situation. Usually we would start with like, you know, how much kinetic energy, how much velocity would it take to escape like a single planet, like just the Earth. But we're diving right in. We've got two planetary bodies that we are trying to escape from. So instead of just, you know, k plus u is equal to 0, we have k plus u from the planet plus u from the moon, right, is equal to 0. So then plugging in our equations, kinetic energy is 1/2 mv squared, right? Our two gravitational potential energies, that those negative signs are going to be important, right? So I've included them there, right? In my equation, you might notice in light blue, that's the gravitational potential energy between the astronaut and the planet. I've assigned an arbitrary like r/2 distance. It looks like in the picture, like the planet's like kind of in the middle of like her and the moon. So she's about like halfway. Or sorry, I should say the planet is about halfway in between the two. So that's what I've assigned as the radius there. That isn't really going to matter. Okay. When we consider like the kinetic energy there, like how is she going to get that kinetic energy? She's got to turn on her jetpack. So instead of saying kinetic energy, like for the way that this question is asked and the follow-up question after this, we can go ahead and just like replace that kinetic energy as like work done by the jetpack. Okay, we algebraically scoot our two gravitational potential energies over to the side. We want to consider the scenario where instead of her being on like the opposite side of the planet from the moon, let's say that she actually like goes to the moon. So if she does that, right, the blue like r/2 distance doesn't really change, right? But for the red one, right, her gravitational potential energy between her and the moon, that is going to change, right? So looking in the denominator, right, our r was originally, right, that whole span, right, from her original position to the moon, which has the planet in the way, right? Then she goes to the moon, so that r, the distance between her and the center of mass of the moon, is going to be greatly, greatly, greatly reduced, right? So that is in the denominator. And so if you have a fraction with a teeny tiny little denominator, that means that the value of the fraction is going to be huge, right? Which means, looking at the context of this whole entire equation, that means that more energy is going to be required by her jetpack to make her escape from this system. Okay. Like I said, this segued very nicely into the next part. So we can invoke the work kinetic energy theorem. So if we're stipulating that she's going to travel at a constant velocity, right, that means that her kinetic energy is not going to change. Okay, and if her kinetic energy is not going to change, that means the total amount of work that's done on her by all of the forces acting on her must be zero. So the force of gravity, right, it's trying to pull her back in. So the force of gravity, we would say, is against her motion. Whenever a force is against the motion, that force is going to do negative work. Okay? Yet, we know that the total work done on her is supposed to be zero. So if there's negative work being done by gravity, there needs to be positive work done by the jetpack, which we kind of established in the previous part. Speaking of nudge, nudge, wink, wink, work, they've made us make a force versus distance graph. So to figure out what the force of the jetpack is, I think, even if you mess this up, I hope that you would still get the right shape. The force of the jetpack ends up being balanced with the force of gravity, right? So those two forces are equal. So essentially, I'm just graphing the force of gravity, which I know the equation for, right? It's gmm over r squared. So in this case, I recognize that the function is like an inverse square, right? So it should have that, it's a smiley face, it's like asymptotically approaching zero, and it doesn't actually hit the y-axis either, because it's like infinity if x is equal to 0. So we also know that, like with this graph, the area of the graph is equal to the work that is done, right? And work is equal to essentially the kinetic energy that is contributed by the jetpack, which gets eaten away by the negative work done by the gravitational force, so that her velocity ends up staying constant. Whew. All right. Last part over here, we're talking about the power requirement of the jetpack. So power is the rate at which work is done. Work is equal to force times distance. So if you do force times distance over time, hey, distance over time is velocity. We've been stipulating that she's traveling at a constant velocity. So as she goes farther and farther away, right, that gravitational force is going to decrease, which means that the required force from the jetpack is going to decrease. And if that force is going to decrease, then, since power is equal to force times velocity, that is also going to decrease. So that's kind of fortunate, because like as her fuel trickles out in real life, she didn't have like this infinite like arc reactor thing going, right? As her fuel trickles out, she will still be able to cruise away from that system at a constant speed.